Hello everyone. Today we are going to discuss the problem message route from CSES Graphs Problem Set. So let's go through the problem. Srijala's network has n computers and m connections. Your task is to find out if Olivi can send a message to Mesa, and if it is possible, what is the minimum number of computers on such a route. So input is, the first input line has two integers n and m, the number of computers and connections. The computers are numbered 1 to n. Olivi's computer is 1 and Major's computer is n. Then there is m lines describing the connections. Each line has two integers a and b, which says that there is a connection between those computers. Every connection is between two different computers, and there is at most one connection between any two computers. Okay. So you need to output that if it is possible to send a message, then you have to first print k, that is the minimum number of computers on a valid route. And after this, you need to print an example of such a route. And you can print any valid solution. But if there is no routes, you need to simply print impossible. Okay. So let's first of all understand what the problem is, and then we can see how we can actually solve this. Okay. So the question is that you are given n computers numbered from 1, 2, 3, 4, 5, 6 up till n. There are n such computers, and there is connection between some computers. Like let's suppose this is connected to this, this is connected to this, then this is connected to this, this is connected to this. There are connections between different computers. What you are told is that a person, Olivi, is sitting over here, that is at computer 1, and Meza is sitting at computer n, that is the last computer. What you need to say is, you need to find out what is the minimum number of computers this Olivi has to pass to reach Meza. This is basically the problem. So if I just take it in generalized way, then basically you are given n nodes numbered from 1 to n. There are connections between nodes, and you need to find the minimum number of steps required to travel from node 1 to node n. This is what the problem is. Like in the current example that I have drawn, there is no possible solution. There is no route you can follow to go from city 1 to city 6, that is the nth city. So over here your answer will be impossible. You have to print impossible. But if let's suppose there was a path something like this, then the minimum number of steps would be 2. This is the path that you can follow. From 1 you can go to 2, and from 2 you can go to 6. So the minimum number, so this path you can follow, and hence the number of computers in the path will be 3, because 1 is also the computer, right? So 1, 2 and 3. So number of computers will be 3, and the path that you are going to follow is, first of all, you are at 1, and then you will go at 2, and then you are going at 6. So this is what you need to print. So I hope the question is clear to each and every one of you. Okay. So how we can solve this? So whenever you get questions like this, that from a single node, you want to get the shortest distance to some nodes. From single node, you want to get a shortest distance from some node. So what is the first thing that comes to our mind? It's Dijkstra, right? Dijkstra algorithm is something that comes to our mind for single node from single source shortest path. Like the source is only one, that is the first node, and from that you want to find the shortest path to every other node. Like in this situation we want it for the nth node, but if let's suppose I want it for every other node, I can simply run Dijkstra and I will be good to go. And this question can also be solved by that. There are two parts of the question basically. Like first of all, you need to print the shortest path, and then also you have to print the path. So we will talk of this printing the path later, but currently talking of the minimum or the shortest path, Dijkstra is something that comes to our mind, right? But over here I am not going to talk of Dijkstra. I am going to talk in Dijkstra. What we do, we use priority queue, right? If you know Dijkstra, what we use in Dijkstra for getting the shortest distance, priority queue or set, something like that, right? But over here, we don't need this priority queue. I will tell you why. Just tell me one thing. If I just consider these edges, then can I say that the weight of all of these edges is 1? Can I say this, that weight of all of these edges is 1, right? Because every time when you go from one computer to other computer, your number of computers, or basically the distance, increases by only 1. So just see one thing. If let's suppose your node's connection was something like this. Okay. You are initially standing over here. So what you will say, the distance currently is, let's suppose I'm counting the number of computers. So if this is my source node, so currently if I am standing over here, so the number of computers is only 1, right? So I pushed 1. Okay. Now what we do? We go to all of its child node and push the distances, isn't it? So for this node, if I go to every child node, if I go over here, then here and here, what are the distances that I will push? For this also I will push 2. For this also I will push 2. For this also I will push 2, right? For all of these 3 nodes, I will simply push the distance as 2, right? And this I will pop. This is the thing I will do. This I will pop and I will push distance 2. Now just tell me one thing. What do I need? What should be the topmost element? The topmost element should be the element with minimum value, right? That is the reason we use priority queue. So the topmost element should be the element with minimum value. So over here, if instead of priority queue, I would be using a simple queue, don't you feel that at the top or at the front, you will always get the element with minimum value? Don't you feel that? And why is it so? This is because the weight of every edge is 1. Weight of every edge is 1. So in these cases, when the weight of every edge is 1, instead of using priority queue, you can always use the queue. Instead of using priority queue, you can always use the queue. Just take this example. Let's extend it a bit more for better understanding. Let's suppose you pick this node with distance 2. Now for all its child nodes, the distance will be 3, right? So 1, 2 will be popped and 2 3s will get pushed. 2 3s will get pushed. But still in front, you will get the element with minimum value only. First of all, you are going to cover these 2 2s and then you are going to move on 3. So the need of priority queue is not there, because what is the reason we were using priority queue? Because we wanted the minimum element distance at the top. That was the reason, right? So if queue is doing the same task for me, why would I like to increase the time complexity by using priority queue? So this is called as kind of 0-1 BFS. Many people would say this. I don't generally prefer these saying this theoretical terms and all, but you should understand that why over here instead of priority queue the queue worked. Because the main essence of priority queue was to give you the minimum element at the top, and since over here the weight of every edge is 1, so 0-1 BFS, that is using a simple queue, will definitely work. So this is how you can simply find out the minimum number of steps. Now let's move on to the second part of the question that we say as answer construction. I have talked of this in the earlier questions as well. We had whatever questions we have solved till now, in that question, in those questions as well, I have talked in depth about these answer construction. This is a very important thing. More and more you practice, more and more good you become in this. So let's see how we can construct answer over here. Okay. Let's suppose we were having these nodes. They were connected something like this. This was node 1, 2, 3, 4, 5, 6. And they were connected something like this. Okay. Let's suppose this was the connection. Now, whenever you are updating the distance of a node, like as you see over here, you were initially standing at 1, right? from 1 you will go either at 2 or 3 at 4. So initially, the distance of every node will be some very big value. Let's suppose 1e9. This is how we maintain distance vector in Dijkstra, right? What we do, we say that, okay, initially let's assume that every node has a very big distance from the source node, and then we slowly and slowly populate the distances. So initially all of them will be very big, and initially this will only have the value 1 or 0. Now from here I will go to either child node, I will go to child node 2, 3 or 4. These are the 3 options I have. When I am going at 2, so definitely the distance to reach 2 will be lesser considering going from 1 than the earlier distance we had. Earlier we had 1e9, right? So from 1, if we go to 2, the distance will be less. So what I will do is I will maintain a parent vector. I will maintain a parent vector, and this parent vector will say me that parent of I will basically say me this ith node came from which node. This is what parent means now. What does parent means? That from where this particular node arrived. So that is what we are going to do. Like let's suppose from 1 we came to 3 and it was the shortest distance. So what I will do is I will update the parent of 3 as 1. Similarly, I will update the parent of 6 as 3. So now once I have the parent, what will be the parent of node 1? It will be 1 itself, right? Because it originated from here only. Now once we have the parent with us, so how we can get to the path? We know the parent of 6, right? We are initially at 6. So first of all, we will write 6. That okay, we have a node 6. We have a node 6. Then we will move to its parent. Its parent is 3, right? Then we will write 3. Then we will move to the parent of 3, that is 1. Then we will write 1. And we have reached to the node from where we originated. Right? So now if you just see, if you just reverse this thing, 136 is actually the path from the node 1 till the node n. So this is how you can actually print the path by maintaining the parent of every node. And this is a very common practice of how you construct the answer in case of graphs and all. So try to practice this so that you become good in this. So basically the concepts that we learned over here is that when we can use a simple queue instead of a priority queue while solving the problem of shortest distances from a single node source. And we have also reiterated over answer construction and the importance of this. So I hope this thing is clear to every one of you. Let's go to the code for better understanding. So this is the code where I am taking the inputs n and m. I am constructing simply the adjacency list where I am taking nodes a and b and constructing the list. I have taken it n+1 because the input is given in 1 based indexing format. Then I construct a distance vector of size again n+1 for the same reason as discussed, since it is 1 based indexing format, and initialized to a very big distance, and initialized a parent vector initially with -1. So initially I am assuming that every node has the parent of -1. Then I am simply using a queue. In my queue, I simply push the first node, that is 1. Distance for the first node will be 1, since we need to find the total number of computers in the path. So first node is also a computer, right? So distance of 1 is 1, and the parent of the first node is that node itself. Now while the queue is not empty, I am taking the front value of the queue and popping it, going over all the child nodes, and if the distance of child node is greater than the distance of this temporary node plus 1, because if you are going to the child node, so what will be the distance? The distance of this node plus 1. One computer is going to get incremented, right? And if the value stored in the distance vector is actually greater than this value, so simply update the value, update the parent for the child, and in queue simply push back the child. Once you are done with this, if distance of n is still 1e9, This means from node 1 you can't reach to node n. So simply print impossible and return. Otherwise, print the distance, construct the answer. Initially the node is n. Simply backtrack from n by taking the parent. While you don't get the node as 1, in answer simply keep pushing back the node and update the node with its parent. Once you're done with this, you have run this while loop till your node was not equals to 1. Once your node becomes equals to 1, you are breaking. So basically node 1 is still not pushed in your answer. So I simply pushed back 1 in answer. My simple answer will be reverse of the answer vector that I have got over here as discussed earlier. Like we were getting 631, but the answer was 136 because we want the path from start till the end. Whatever we have got till now is actually the path from end till the start, right? Okay. So simply reversing the answer, printing the answer, new line, and we will be good to go. So this is a very classical problem of Dijkstra where instead of using priority queue, we were using queue, and also we were updating the parent and printing the path. So I hope all of you got it. Thank you.